There you
So
go.
brilliant. Amazing. It's always been, every time it works, one's still very impressed, isn't it? Let's just see if I can actually, can't see myself. That's all right. I don't need to see myself. Okay. Right. I think I'm set up now. And thank you very, very much. This is really, really exciting. And thank you very much, Brian and Robin, for those incredibly kind words. I don't think that I can live up to them, but I'll try. I really do wish we were all in Toronto. I was really looking forward to seeing you all, and especially seeing all those beautiful slides of tactile and emphatic artworks. I really wanted to be there, see them in the real, but we can also have a fantastic virtual experience, and I'm really looking forward to all the other talks this week. I want to talk about color and light too, beginning with going all the way back to MIT in the 80s, Brian, and to David Marr's very prescient observation that we can tell just by looking whether a fruit is ripe, whether something very odd is happening, whether a leaf is green and supple, whether an insect is likely to be poisonous. And all this we do through color, whether a person is healthy or unhealthy, attractive or unattractive. These are the things that color does for us. And in saying this, David Marr articulated a view, which is, I think, widely held now, that we evolved color perception not simply to recognize objects, but to guide our behavior, and to do so by eliciting motivational drives. So here, shape is enough to enable us to recognize this banana and to discriminate it from an elephant, but it's not enough to motivate us to eat them. And taking red as a further example, red is what motivates to pick these berries. It signals their ripeness, or to avoid this toadstool, it signals its toxicity. Red signals sexual readiness in this female baboon's red rump. So red has acquired this meaning from its biological purpose. So we find red stimulating, arousing, attention grabbing because of the function that it's served in signaling key material properties that guide our behavior. And we see color because light interacts with particles and surfaces, and then with the sensors in our eyes. And from this interaction, we then conceive of color as a representation of the meaningful properties of objects. So the glossy red of the apple here signals its edibility, the nutritional richness of its juicy flesh beneath its taut skin. The banana, likewise, is fresh and ripe. But to extract this meaning from the light that enters our eyes, our visual system must unpick the interaction between light and surfaces. It has to perceive stable colors by disentangling changes in illumination over space and time from changes in object properties. So the change in the banana, as it undergoes changes in the illumination here, the changes in its color appearance are not meaningful because they are caused by changes in the illumination. The yellowing of the banana skin is only meaningful to us when it comes from actual ripening changes in the pigment composition, or so we think. And so much of color constancy and color perception is framed today. It's all about the object and how the color appearance signals material properties of the objects. The question I want to pose today is, what meaning do we conceive from the illumination itself? So when we conceive of color, what do we do with the light? And many painters have, of course, been deeply concerned with seeing and representing light, not only with representing the meaningful color of objects. So here in this painting by Claudio Bravo, you see fine gradations of cyan in the tablecloth caused by variations in illumination, interreflection, shadow, and shading. And our visual system is able to dissociate the uniformity of the material here from the spatial play of illumination and read the tablecloth as a single surface reflectance. Claudio Bravo was an amazing hyperrealist painter of the 20th century. If you don't know his work, do look it up. Very different from Claudio Bravo's works are Hockney's early works. In his early days, there were only objects and surfaces, almost no depiction of light. Light is almost an incidental necessity. Without it, there would be nothing to see, but it's only the things he sees that he paints, not the light itself. Here, the buildings and pavements are almost Mondrian-like in their rectangularity and flatness. There are no cues to the illumination, no shadows, apart from one long rectangle you can see stretching beneath the overhang of the roof, and a gray parallelogram under the deck chair. The sky and water are both blue, but it's blue in and of themselves, as if the light shining on them was perfectly neutral. And then, as Hockney says, of a painting he did in 1967, I realized the light in the room was a subject, and for the first time, it became an interesting thing for me, the light. And here in Sur la Terrasse, the evening light is all conveyed by shadows. Interestingly, the shadows formed when the grazing rays of direct sunshine are blocked by the railing are deep, are bright blue, not dark as shadows should be. And there's much more you could say about this wonderful painting, the resonances between the cerulean blue and the rose pinks. But it illustrates Hockney's burgeoning interest in light. And of course, Monet in his series paintings captured the illumination itself. Here, depicting not just the manifest solidity and durability of the cathedral stone, but instead the change in illumination on it from early morning on the left to full sunlight on the right. And in a sort of homage to Monet, in his most recent The Arrival of Spring series, just shown at the Royal Academy, Hockney now also paints light as if it is a thing unto itself. In 7 paintings, he paints the same distant hill beyond a tall tree and some spherical shrubs, and the sky and the illumination color changes through inky blues to mauves to rose pink as the sun moves through the sky, as it were. So he's really capturing the effects of light as well as the constancy of objects and celebrating the colors as they feed our emotions. But what does it mean to say that painters are painting the light? Are they only painting the effects of light, as here, highlights, shadows, shading, the interaction of light with 3D surfaces, or are they painting the light itself? In this painting, you see all those effects of light, but you do not see the light itself. And I think that contemporary artists, in particular Sean Scully as a prime example of these. He was a fine art student at Newcastle University in the 70s, and now, as he says himself, he's the highest paid living artist in the world, has taken this sort of to the extreme, saying the painting itself should be the only surface in and of itself, with no illumination within it, and no sense of illumination even within the viewer's space. The light should illuminate the present and the painting and not be present. So, but here, though, after that long preamble, I will get to it, my main topic, which is talking about the light that illuminates things and that brings things into being in our minds as we conceive of their color. And I'm really talking about whether we can see or feel the illumination in space that enables us to conceive of colors. And this really follows a long line of historical, often philosophical debate on whether we see or feel or infer the illumination, as James Schirillo put it in his wonderful essay, 2013. Schirillo said very boldly, Helmholtz was wrong. We do not infer the illumination only to discount it and judge the constant colors of objects. Instead, we encode the illumination and take it into account in a sort of iterative process when constructing lightness and color. And I'm sort of plugging our chromatic mock card illusion here to say that this is an example of the interplay between reconstructing the illumination, here the mutual illumination between the two sides of the cards, and the reflectance of one side of the card. The right side of the card here changes from white to pink, depending on the shape that you perceive that card to be and whether or not you perceive mutual illumination to be happening between the two sides of the card. More recently, from the work of the Delft group, Jan Kundrink, Sylvia Pont, and others, we now know that people do behave as if they carry a representation of the light field filling the space within their minds, suggesting that Kafka was really right when in 1935, he said that the intensity of the lighting of space is not really seen, but felt. So in some way, we have a sense of the illumination. And this is the question I'm asking. Do we directly perceive the illumination? What is that sense that we have of the illumination? So let's come at this from the point of view of color constancy. This is my favorite illustration of color constancy, which I basically got way back in 2013 at the previous AIC from Roy Burns, or rather from his wonderful book. And it is, color constancy is the fundamental perceptual phenomenon that enables us to see these lemons as yellow in this painting by von Holzdunk when it's illuminated by blue light. And we see them as yellow when the same painting is illuminated by white light. And yet, of course, the actual reflected light from the central lemon when it's under blue light is so different as to turn it into a line when it's placed into the context of the painting under white light, as Roy Burns illustrated. And then, although this also illustrates that although the color appearance of that lemon does change, it's not perfectly constant. The key is that we recognize the lemon is staying the same and the light changing rather than the other way around. And now, in contemporary computational vision, the computational problem of color constancy is framed as a problem of recovering an invariant descriptor of the surface reflectance of the object. And this means disentangling from the reflected light of the object the separate contributions of the illumination spectrum and the invariant surface spectral reflectance of that object. Now, when the light on the object, here a green apple, changes from Madrid morning spectrum to northeast of England evening spectrum, the light reflected from the object changes. And at the back of the eye, of course, in the retina, the three distinct cone types sample that reflected light and therefore respond with two different sets of triplet of cone responses to those distinct spectra of reflected light from that object when it's under distinct illuminations. And thus the color constancy problem as a computational problem can be framed for the human visual system as how can the human visual system reconstruct a set of invariant, set of constant descriptors, three descriptors from that set of variable cone responses in the retina in response to a constant surface under changing illumination. And of course, in machine vision, computational vision, and in color correction algorithms, indeed, the problem is framed similarly. How is a set of set of RGB values from a scene under a test illumination transformed into a set of RGB values of the same scene under a neutral illumination? So the notion is that in some way, both machines and humans have to reconstruct the scene as it would appear under a neutral illumination, and that will be the set of constant descriptors. Now, this is both an ill-posed problem and an ill-defined problem. Ill-posed because there isn't enough information in that set of cone responses to recover absolute reflectance or illumination. And it's also ill-defined because we cannot precisely define what the actual appearance would be to a human viewer of a complex scene under an unknown illumination. We simply don't have good enough measurements of color constancy in humans. And that's partly because human color constancy itself is highly variable, although people have a sense that object color is a meaningful, stable property of objects. The actual color appearance of objects varies widely, and human color constancy varies widely between individuals and depends on the illumination, the surfaces, and the experimental paradigm. So just to say, as a kind of an aside, indeed, right now, we're currently trying to understand color appearance of complex scenes under multiple illuminations. So, for example, we take a scene like this, we illuminate it with two different light sources, so a gradient of illumination comes across it, creating a scene with multiple illuminations, which is particularly challenging for color correction algorithms, as Brian well knows. He's one of the leaders in the field of dealing with this. But getting the measurements of what such a scene actually looks like to human observers, and therefore what a color correction algorithm should try to reproduce, is another story, and that's for another talk. But perhaps the best example of the individual variability in color constancy comes, of course, from that famous dress. And I will just play a little clip here.
That dress.
That fucking dress.
Apologies.
Froze over this dress.
Blue, white, gold. Oh, yeah. Black and blue.
Is this dress blue and black? Or white and gold?
Oh,
It's fucking awful.
Okay, this was a little clip from Gogglebox filming this family watching a science program in which we, people in my lab and myself, talked about the dress. But people really argued over the color of that dress, and that is because of differences in their color constancy mechanisms, as I'll come back to right at the end. But one reason why people differ so much in their color constancy, i.e. in the way they perceive object colors under changing illumination, is because they come to these scenes with different prior expectations, different prior experience, and therefore different influences from higher cognitive processes that therefore influence their color conceptualization and constancy. One factor is memory color, so the colors that people remember familiar objects to be. And memory color is that thing which tells us that these bananas are somewhat weird and there's something wrong with this strawberry. It's what tells us that there's something right about this apple. Now, in work by Milena Vuro for her PhD thesis, she showed that actually memory color is made more accurate and more less variable by the inclusion of texture in the stimuli that elicit memory color. Other experiments have showed that memory color does influence immediate perception. So Torsten Hansen and Maria Okkonen and Carl Gegenfertner showed that people's achromatic settings differed for a banana shape versus a disc. So that when people adjusted the shape of a banana to appear gray, they had to add more blue than they did when they adjusted a disc to appear gray, as if they were having to cancel out the yellow color, which was their memory color for that banana. Other memory color effects have been shown. A fascinating one is the one shown by Rosa Leifer-Sousa, pictured here, Bevel Conway, that under sodium light, when all other surfaces, including the skin on the body, looks gray, faces look green. So there's an influence of one's memory color for what faces should look like, which makes faces turn green when they're seen under very impoverished illumination. These effects illustrate the fact that memory color for familiar objects are affecting our immediate perception. Edvard Munch called on memory color, I argue, to shock us into seeing something very wrong with this face. And here we also see a demonstration of the importance of color in signaling behavioral state. So, because remember, for color to be meaningful, a change in color appearance has to signal a change in material properties, not just a change in lighting. But here we assume that most people were living under natural light, not sodium lighting. So the green of the face here is signaling something meaningful, in this case, jealousy. So what we want to know now is, does human vision know that it's not living under sodium lighting? Does it embed knowledge of natural illumination, and in what way? And what does that have to do with color constancy? So I want to just have a little section here on what the characteristics of natural illumination are, and to illustrate this with a few measurements that we and others have taken recently. So we evolved under natural illumination. We humans evolved under daylight, which is broadband and has energies at all wavelengths and has spectra that take characteristic shapes. It's a mixture of directional sunlight and diffuse skylight. And here we see examples of different spectra at different times of day measured in the north of England. Here at one point in the morning, we see the two different components of that natural daylight, a directional component on a cloudy day and a diffuse component, which is more neutral in chromaticity. Now, this variation in the mix of the directional and the diffuse components leads to a systematic variation in chromaticity of daylight, which we know is the daylight locus. This is a very well-known fact, that the chromaticities of daylight fall on a locus which is very close to the Planckian locus, the locus of chromaticities of a black body radiator. But this, this closeness is actually accidental because it doesn't have anything to do with the solar temperature, which is actually unchanging. But this chromaticity locus of daylight chromaticities is deeply embedded in our psyche, and it comes out in visual art too. Shown here in Turner's color beginnings, the chromaticities of which fall almost exactly plotted here on the daylight locus. So we can first ask, does human color constancy embed knowledge of spectral variations in natural illumination? Is human color constancy in some way optimized for or tuned for these spectral variations in daylight from bluish to orangish? We can see clearly this variation in illumination color across the day in this series of photographs taken from the same location at different times of day in January 2019. And you see the white snow varying from a sort of yellowish to bluish over the course of the day, capturing the change in chromaticity of the illumination. And yet all of these chromaticities are perceived as white. When people are asked to actually adjust, say, patches on a screen to be achromatic as a way of estimating what they perceive the current illumination to be, or as a way of perceiving, accessing what their internal whites are, what you find is that people's matches vary most along that daylight chromaticity locus, as shown recently and very nicely by Jenny Boston Beer and Don McLeod. So our internal knowledge of what's white seems to reflect an internal incorporation, internal knowledge of the chromaticities of daylight. May we ask, and now we ask whether our human color, our constancy of scenes as measured in experiments also incorporates this optimization for daylight chromaticities. And in a series of experiments using what we call the illumination discrimination task, we ask people simply to judge whether the illumination on a scene has changed or not. And in this experiment performed in what we call our Newcastle light room, people view a Mondrian inside a box under one illumination generated by spectrally tunable lamps, which can generate an infinite variety of spectra matching exactly any daylight chromaticity or other chromaticity we would like. People judge whether the illumination on the scene has changed, and we then alter the illumination in different directions in color space, either along the daylight locus or along directions orthogonal to the daylight locus. So on a given trial, a person sees a reference surface like this under one illumination and says, does the first or the second illumination match the first? And in this way, we can measure thresholds for discriminating illumination changes. And we find that people are consistently much less able to see changes along the blue-yellow direction compared with changes along the red-green direction. So there seems to be a bias towards having better color constancy along the daylight locus, and in particular for bluish illumination changes, because being unable to see the illumination change equals having better color constancy. There appears to be no change on the scene despite the fact that the illumination has changed. And this blue bias is illustrated here by a plot of the thresholds in different color directions from a neutral point in color space. So the thresholds are smaller in the green-red direction and bigger in the blue-yellow direction and biggest in the blue direction. And this so-called blue bias is something that we've demonstrated with multiple versions of this task and simulated in real scenes and multiple venues, including in the National Gallery in the Making Color exhibition, where we got responses from 1,800 people and showed a consistent insensitivity to changes in the illumination in the bluish direction relative to other directions. Now, we did the same experiment starting from not a neutral illumination, but starting from chromatically biased illuminations. And sort of just to cut to the chase, we found a particular pattern, which was that changes in illumination that were going away from the biased illumination towards neutral, that's say the longer arrow here in the green direction from a red starting point, were much harder to see than changes away from neutral. But over all of these different illuminations, changes in the bluish direction were again hardest to see overall. So it appears, and this is sort of cutting a long story short, that the human visual system is assuming a gray world and a bluish daylight, and using those assumptions to guide its color constancy conceptions. Another recent experiment that Becca Wedge-Roberts and together with others at Durham and myself at Newcastle performed illustrates, again, this blue bias in color constancy. It also illustrates the individual variability of color constancy. And in particular, Becca was looking at the development of color constancy. So she measured color constancy in young children using this task where she asked them to match Derek the Dragon's suite to the suite under a different illumination. So pick the square that matches Derek's suite on the right side. And color constancy was measured by how close that match was to the color it would be if it was actually the same reflectance as the one on the left, but now placed under this new illumination. And different suite colors were used and different illuminations were used. And again, to cut to the chase, the color constancy indices, so the closeness of the match to the correct reflectance, were highest for the bluish illumination and lower for the other illuminations. Now, the fascinating thing about this experiment, and for which we don't yet have a complete explanation, is that the children were slightly better in their color constancy, these dark violins here, than the adults, measured in this way. And their color constancy declined from about age 6 to about age 12. But what you'll also see from the spread of dots here, each dot being a different individual and condition, is that people vary hugely in their color constancy. So this is another reason why it's very difficult to create color correction algorithms that reproduce what people would actually see if they were viewing that scene. So that's a couple of experimental results that suggest that human color constancy incorporates knowledge of the spectral variations of natural illumination. And the next question we want to ask is whether human vision follows temporal variations in natural illumination, because although I've talked about the daylight locus and the way daylight changes in chromaticity, what I didn't talk about is what the temporal profile is of those changes in chromaticity. The temporal dynamics of natural illumination are also very regular and predictable. As the sun changes its elevation in the sky, the illuminance, the overall lux of the illumination changes in a similarly smooth way, peaking around noonday and then falling. That's true on a completely cloudless day. This is from a database in Spain. These are from direct measurements made by Ruben Pastilla on a hilltop in Newcastle last October. And what you see is that instead of this smoothly increasing and decreasing change in lux, we have a much more jagged change in lux over the course of the day from 7 a.m. to 7 p.m. And that's because that smooth change in illuminance is interrupted by wind and cloud that changes the lux. But you'll see that the color temperature of the light stays largely stable over the course of the day. And this just little video shows you how quickly the overall lux can change in Northeast England. This is on another hilltop in County Durham. As the wind blows and the clouds move through the sky, you have very rapid changes in the overall lux. But this pattern of lux and chromaticity changes during the course of the day are very characteristic, and not just in Northeast England, but also in the west coast of the USA. You see the same sort of rough increase and decrease in lux over the course of the day. And here's seen most clearly a rapid change in chromaticity at the beginning and the end of the day. At dawn, decreasing blueness and increasing brightness, and at dusk, increasing blueness and decreasing brightness. So this is a tripartite pattern, which is characteristic all over the world. And here again,
Sorry, Anya, we're sort of at the 10-minute to go.
Oh, we're at the 10-minute, right. Okay, good. Well, I'm going to just finish this little section and then I might conclude early. How's that?
It's fine. It's just a matter of how much time we have for questions and stuff. So
yes, okay, great. So what we see here is the velocity of chromaticity change over the course of the day, and the fastest chromaticity changes occur at sunset and sunrise, and also in the when the lux is darkest. So the color of the arrows here represents the brightness. So darker arrows are darker luxes, and here we see that the in the very high lux levels, the chromaticity is mostly stable. The most rapid changes occur when the lux is lowest in the morning and evening. So what we were interested in was whether people are actually able to see these natural changes in chromaticity of light. So we measured people's ability to see smooth, slow changes in illumination like those that would occur at dawn and dusk using these spectrally tunable lamps. And people sat in a white room and the light changed in a linear ramp from a baseline level to another chromaticity along the daylight locus, starting from either a very bluish baseline or a very warmish baseline. And what we found, and this is Ruben Pastilla's PhD work consistently, is that changes towards neutral were much harder to see than changes away from neutral. So for a bluish light, changes in the yellowish direction were much harder to see than changes in the bluish direction. And these results are for lights at a constant luminance without any change in luminance. So it doesn't mimic the actual changes in daylight where also, of course, lux is changing. So more recently, we've incorporated luminance changes as well, so that people were asked to report whether the illumination had changed or not for changes in chromaticity alone, changes in lux alone, or changes that incorporated both chromaticity and lux. And unlike for the previous experiments here, instead of being in a white room, people sat in a room filled with chromatic surfaces. And we found again the same pattern of results, that again, starting from a cool illumination, changes in the warmer direction were much harder to see than changes in the cooler direction. Changes in luminance were easier to see, so lower thresholds than changes in chromaticity alone, but this same pattern of a difference between a sensitivity to warmer versus cooler directions held for the changes that incorporated lux changes as well. And what these results suggest overall, that the natural changes in chromaticity and lux in the early morning are more difficult to see than other changes. So when the light is becoming yellower, as the light is becoming brighter, starting from a dim blue light of dawn, those changes are difficult to see. And in fact, the threshold for seeing those changes is much higher than the actual changes. So the changes that occur are too slow for us to directly detect them. So even when the changes in chromaticity are most rapid, these are very difficult to detect. So it does appear that the human visual system is optimized to dampen its sensitivity to the largest natural changes in illumination. And this, we propose, is in order to maintain perceptual stability of object color, because these are the lights and the types of changes that we grew up under. So the resultant perceptual stability of the scene then transfers to the illumination itself, and we don't see those changes in illumination. So we can then ask, how is it that people possess a general awareness of temporal changes in illumination? How do they feel the illumination, as Kafka suggested? And people sitting in the Lightroom say, I felt that the illumination had changed, although I did not notice it at the time. And Mike Murdoch has reported similar results from his experiments. Now, I think I'm just going to try to quickly say that because of the duality of the human response to light, we have visual responses to light, but we also have non-visual responses to light via the intrinsically photosensitive retinal ganglion cells, which contain melanopsin and which respond directly to light. And just to cut to the chase, we suggest that it's via those melanopsin-containing retinal ganglion cells that we sense changes in the illumination. And these intrinsically photosensitive retinal ganglion cells complement the blue-yellow pathway, which was our primordial light detector, which evolved into our object detector together with the evolution of the red-green pathway. But those S-cone cells feed not only that those visual cells in the retina, but also the non-visual IPRGC. So the IPRGCs receive input from the S-cones. They project to the suprachiasmatic nucleus, where there are neurons that actually respond to this cone-opponent modulation. And the changes in melanopic lux over the day actually exactly follow the changes in photopic lux. So the cells, the intrinsically photosensitive retinal ganglion cells, have all the properties necessary to follow the temporal changes in both chromaticity and irradiance of daylight via the input from the S-cone cells and the melanopsin cells. And they also sit in the front of the retina, so they're closer to the entrance of light than the photoreceptors that feed our conscious visual pathway. So it's very likely that this sense we have of changing illumination is provided by the non-visual system, which then projects throughout the brain, governing our mood and circadian rhythms. And from this sense of the illumination, we can read things like the time of day, the weather, the season, critical factors which influence our behavior on multiple levels. I was going to talk briefly challenges from violations to the natural way, which occur from this kinds of novel illuminations that we're under now. But one challenge is, how do we capture the look and feel of illumination images when we're applying color correction algorithms that are trying to eliminate the illumination? It's an important thing we must consider when developing our digital photography. How do we cope with metameric lights, which alter the appearance of chromatic surfaces, but not the appearance of neutral, achromatic, spectrally non-selective surfaces, we're exposing ourselves daily to artificial lights, which are no longer broadband like daylight, although they are metameric to daylight when reflected from white surfaces, and they therefore can alter the color appearance very dramatically of artworks, for example. But these alterations can be exploited if we wish to bring out differences in material properties and enhance, for example, the redness of the Virgin's robe here. And this is my last slide. I did just want to finish by saying the other reason why that dress has evoked such different responses in individuals is because the chromaticities of the dress fall along the daylight locus and therefore create additional ambiguity as to what is illumination versus what is material. And indeed, when the inferred illumination chromaticity is measured in individuals who see the dress differently, we find that those who see the dress as blue and black infer the illumination to be bright and yellow, whereas those who see the dress as white and gold infer the illumination to be dim and blue, demonstrating that both the inherent embedding of the spectral characteristics of natural illumination and the inherent variability of color constancy. So bottom line, we conceive of color by subconsciously knowing and feeling the illumination. Thanks, and sorry to have gone a little bit over.